Chapter 8.2, we're going to discuss an integration technique called integrating by parts or integration by parts. This is the most useful for integrating products of either algebraic or transcendental functions. Right, so functions that are, or integrands that are more complicated than those that we can simply find antiderivatives for directly, or even use substitution. It's not simply just a chain rule occurring there. We actually have a product usually. So what I'd like to start with is the actual equation that we're going to end up with. So I'd like to show you this. This is what we're going to end up with, and we'll discuss kind of the steps here in a second. But we have some integral that looks like this. It's some product of either algebraic or transcendental functions, and it's one that we can't directly integrate. And we can use this formula. If we designate one part of this integral as u and another part of it as dv, then we can find u and v and find the product of those two things, and then subtract the integral of v du. Assumedly, this integral is easier to find than this one. Otherwise, there isn't much point in using this. So we're assuming that we found some combination of factors here that we can now actually do this integration, or at least proceed in some other way, another step along that path. So let's see where this comes from. All right, we need to know this by heart. So this is something that when we do each example, I'm going to kind of say, okay, well, let's rewrite this so that we really burn it into our brains. But let's take a look at where it comes from. If we start with the idea of the product rule, so just taking the derivative of a product of two factors. These both are probably functions of x, right? So we do u times v prime plus v times u prime, or u times dv dx plus v times du dx, right? So we can write it either way. All right, so we're really just writing down the product rule there. Okay, so we're going to start with that, and then we're going to integrate both sides with respect to x. So I have this derivative with respect to x of uv. When I integrate that, of course, I just get uv. Now when I integrate both sides over here, I have the integral of uv prime dx plus the integral of the u prime dx. All right, and I can define dv as v prime dx, so that is this part right here. And the du is u prime dx, so that takes care of this part right here. All right, so what I end up having is I have uv equals the integral of u dv from this first part here, plus the integral of v du from the second part of that sum. And then if I just solve for the integral of u dv, so I subtract the integral of v du, and I get what we know is kind of the formula for integration by parts. All right, just seeing that happen, it's not exactly clear how that's helpful, and we'll have to kind of look at some examples to do that. The next question becomes, if I see a given integral, how do I decide what to make u and dv? So in a similar way to when we do u substitution, what was that, back in chapter 4, we had to think about, okay, well, what are we going to make u? What are we going to set u equal to for this to work? With integration by parts, we have to think about what are we going to make u, and what part of that integral are we going to make dv. So here are some suggestions for that. Right, so we try to let dv be the most complicated part that fits a basic integration rule. Right, and the reason for that is because after we choose u and dv, we need to integrate dv easily in order to find v. The v that goes both in this product and as the integrand here. Right. So assumedly, we want that to be an easy antiderivative. And then u is going to be everything that's left over, all the leftover factors that are part of that integral. Right. For u, we're going to try to pick a u so that the derivative of u is simpler than u itself. Right. So here I'm trying to integrate u, and here's my du. This is the differential, at least, of u. And the only way this change really helps me is if the du is simpler than the u used to be. Right. And if we use that, then the dv are going to be the leftover factor. The dv will be kind of encompass all the leftover factors there. So the general rules are the dv is something that's easy to integrate, and the u prime must be simpler than the u itself. Right. There's a little mnemonic that I think is sometimes helpful in choosing your u and dv. So this is a mnemonic for choosing u, for which part of that integral you're going to let be u, and it's called liate. It's L-I-A-T-E, liate. And so we're going to try to let u be the logarithmic part, if there is one, of the integral. If not, we're going to try to let u be the inverse trig part, if there is one. If not, then we're going to try to let let u be the algebraic part, if there is one. If there isn't, then we'll try to let u be the trigonometric part, and we'll finally, if we have no other option, then maybe u will be equal to the exponential part. If you think back to this idea that we talked about in the last page of we want the derivative of u to be simpler than u itself, you can kind of imagine why these are the last choices that we would make, right? If I start with a trigonometric function, say like sine of x, and I take the derivative of that, well, I get cosine of x. That's not particularly simpler than sine of x was when I first started, right? If I let u equal an exponential function of some sort, and I take the derivative, well, the derivative of e to the x is just e to the x. That's not any simpler at all than it used to be, right? So these are kind of our last choices for u, to a large degree, because when we take the derivative, it doesn't simplify things for us a whole heck of a lot.